This video is about understanding reaction conditions. So in Chapter 1 of Organic Chemistry, you're introduced to different acids and bases, and Bronsted-Lowry acids and bases. You're introduced to pKa's and how pKa's are the negative log of your Ka value, and your Ka value is your products over reactants, and it's an acid-base reaction. Now, my concern is one, the reason why this is given to you in Chapter 1 is you got to understand the concepts. But then in Organic 2, you really got to be able to recognize acidic protons. We need to recognize acidic protons in the organic structure. We've got to recognize the strong bases or even acids that are in your reaction. And then we need to be able to look at pKa tables and figure out what's going to happen in that flask. So for my students, you guys, I have given you pKa tables and we have been practicing this. And I am going to quickly review some of the reactions that we've done where we look at the pKa values and try to figure out the equilibrium of the reaction. But the first thing I'm going to do is I want you to recognize your strong bases. Your strong bases are anytime you have a carbon bonded to a metal, okay? And your metal typically is magnesium, which are your Grignards, so you'll see magnesium bromide. You might see in a lithium. So if you see MgBr, that is a base. If you see, this is cyclohexyl lithium, that is a base. Now it's also a nucleophile, but what distinguishes a nucleophile? If there's an acidic proton around. So if there is an acidic proton on your organic compound, then this nucleophile will act as a base. And the reason why that happens is because it is so much easier, quicker, kinetics, faster to obtain a proton, an acidic proton, than it is to act as a nucleophile and attack like a carbon. So anytime you see any of these carbons, so when I see a metal, you just go ahead. I mean, it's electropositive. These are magnesium. That's an alkaline earth metal. Alkali means base, okay? Alkali, lithium, alkali metals. So you make that a plus. And what happens is then your carbon is a negative. And essentially what you have here is a carbon that has these two lone pairs, this lone pair and negative charge. Now, if you have any kind of acidic proton, so now you got to recognize what an acidic proton. Well, water would be considered an acidic proton. So what's going to happen is these electrons here will come and deprotonate. And then that becomes a carbon hydrogen, and you generate this OH. And the magnesium bromide then hangs out with the OH. And what we've been doing in class is we've been circling so if you have a reaction like this, which is in one of our quizzes, and you have water, the goal was to figure out which way the equilibrium goes, and then this becomes H, and then over time this becomes magnesium hydroxide, actually. Okay, so your acidic proton then is here, and your acidic proton is here, and you compare the pKa values, and so you have a pKa table, and you see that's 15.7, and you see the pKa of a hydrocarbon, and I've told you to go ahead and highlight some of these that you're going to see all the time. So I look here, and I see hydrocarbons on page 3. And you're not going to find the exact one, but it is just a regular, what is this? This is an sp3 carbon. And an sp3 carbon has a pKa of about 50. Okay, so you can review what a pKa means, but in our world, the higher the pKa, the weaker the acid. So if you look at some pKa tables, you know that HCl is a strong acid. HCl has a pKa of about -7. -7. So the lower the pKa, the stronger the acid. So you can imagine this pKa here is 50. So that means the reaction is going to go towards the weaker. Okay? The reaction equilibrium goes towards your weaker acid. Your weaker acid is 50. So you make a little arrow going towards the left and a stronger arrow going to the right. Okay, so you got to recognize these strong bases, and you also got to recognize your acidic proton. Now, other strong bases. Strong bases are alkoxides. Alkoxides can be like methoxide. And a lot of times you'll get like a sodium methoxide. You could have ethoxide. And what happens is the oxygen has a negative charge and the sodium here has a positive charge. How these are made, you basically take sodium metal in a solution of, so this would be a solid, in a solution of like methanol. And what happens is then you get CH3O minus sodium plus, and this hydrogen here is your acidic proton, and it will become hydrogen gas. And to balance this, a lot of times 1/2 is put there. So you can imagine 2 react. And okay, so if you look at your pKa tables and the pKa tables that I've given you, you can see that the pKa of that acidic proton is, any alcohols are 16 to 18. Look at your thing, whether they're branched. So you got about 16 to 18 pKa, and then your hydrogen gas is about 35. Okay, so basically your equilibrium arrow is going to lie more to the right, and it's going to form hydrogen gas, and you're going to make this methoxide in the presence of sodium. And that's one of the reasons why you get used to seeing, if you see a sodium metal or you see a potassium metal and you see an alcohol in solution in your reaction arrow, you need, the first thing that will always happen will be the forming of this metal alkoxide. So that's the first thing that will happen. And you need to know what's going to happen first, because as you see, you get reaction 1, 2, and 3, and you've got to be able to figure out what's going to happen. So this is the first thing that's going to happen whenever you have an alcohol with a sodium or potassium. Like I said, if you see these organometallic type compounds, you need to start understanding these are considered basic conditions, because if there is an acidic proton in solution, that is the first thing that's going to happen. Now, how do you recognize? This is important. You need to recognize acidic protons in your organic compounds. Other strong bases, by the way, would be like sodium hydroxide, because there's your plus and there's your minus. So look for your metal and the O minus. Okay, acidic protons. Acidic protons are, in organic chemistry, we've talked about alkynes. So a terminal alkyne has an acidic proton, and that shows you a pKa of, I want to say 25. Let me look, because this is an SP. And we've talked about why that's acidic, because it's an SP, and in my chart it says 23. So we'll just erase that and write 23. The other acidic proton that you're going to come across is alcohol. We've talked about those. So anytime you have an alcohol, you notice this is connected to an oxygen that has a pKa of about 15. Oh, I'm sorry, what did I say? That's going to be about 16. Remember, 16 to 18? But we're getting ready to get into phenols. Phenols are different. So if you see, this is a cyclohexanol, cyclohexanol. This is a phenol. Phenols have a pKa of about 10. And this is cyclohexanol is your alcohol. It has a pKa of about 16 to 18. So what happens here is if you throw in something like sodium hydroxide, which is a strong base, and you do your acid-base chemistry, so you have to find your acidic proton. There's your acidic proton. It's connected to the oxygen. In this case, this would be your acidic proton. It's your most acidic proton. Then your base would come. Here's your plus and minus, your oxygen. The base would come and take the proton away, and you would make alkoxide, a phenoxide. So this would be called a phenoxide, sodium phenoxide. Now, you would also make water. So when you're comparing the reactant side and you're comparing the product side, what are you comparing? You're comparing the pKa. So you got a pKa of 10 for this proton here and a pKa of 15.7 for water. So your equilibrium will lie towards the sodium phenoxide compound. So that means that you can take phenols, which are different alcohols, and throw in sodium hydroxide, and you can get a sodium phenoxide. Now, if you do cyclohexanol and you throw in sodium hydroxide, you will find that the pKa is not going to go so well. So if you have that there and water, you're comparing a 16 to 18 to a pKa of 15.7. So you're going to have more of the cyclohexanol than you would the alkoxide. So that's why strong bases are typically used in deprotonating just regular alcohols. So you usually find sodium amide, and that's written sodium amide, and you have to just kind of memorize that. Sodium amide. You also will find just plain sodium metal and potassium metal. So let's look at even our alkynes. So alkynes, you all know that this sp hydrogen is an acidic proton. So when you have sodium amide in a NH2, you do get CH3, the sodium acetylide. So you're getting your acetylide. And then what's this make? This makes NH2H. And then this acidic proton has a pKa. If you look at ammonia on your sheet, I want to say that it is 35. I will look. Probably nitrogens, ammonia. So, and I would recommend you highlight these so you don't have to do what I'm doing every time. Maybe they're inorganic, yes. So here we have, you gotta be careful, there's HN3. I'm looking for NH3. I'm just gonna, for time's sake, I'm gonna put 38. I think that's what it is. Okay, so if you look at that, it's going to be more towards the 38, which is your weaker acid. And we said that this pKa for this, a proton, is going to be more like 23. So what's the difference between 38 and 23? 38 minus 23 is 15. That's 1 with 15 zeros. Okay, so that's a rate faster that this is going to happen in equilibrium. Okay, so hopefully by now you're recognizing these strong bases. And so when you see these in reactions, you need to recognize that that's what's going to happen. The other acidic protons. So we've said that a terminal alkyne has acidic proton. We've said that alcohols have acidic protons. So, but it has to be, these have to have strong bases. We'll call them strong bases. So strong bases are like sodium metal, potassium metal, or sodium amide. Okay, those are strong bases. We've also talked about phenols. This is an acidic proton, and we'll just call this a strong base. And a strong base is like sodium hydroxide. Also an alkoxide could do that too, and you can work out an alkoxide pK on that. All of these, a strong base would be like an organolithium, so we'll just do CH3 magnesium bromide. That would depronate. That's a strong base, and that would depronate those hydrogens. Let's go to the next slide and see what kind of acids. Well, before we do that, I want you to recognize strong acids. Strong acids are not so hard because you see HCl, HBr, HI. These all have pKa's of -7. Hydronium, you see that written across the reaction arrow. That pK is a -1.7. If you see something like acetic acid, that pKa is about a 3 point, or that pKa is about 4.74. So these are acidic conditions, and under acidic conditions, anytime, this is important in organic chemistry too, because you're learning a lot of new reactions. Your functional groups, okay? We got to know our functional groups. That was also introduced to us. This is a carbonyl, okay? That's a carbonyl. Carbonyls have a carbon that's delta positive, and the oxygen is delta negative. So there's this pull of electrons towards the oxygen from the carbon. It makes it positive. Now, this can get further activated under acidic conditions. So a lot of times you'll see hydronium conditions. The first thing that's going to happen is you're going to get protonation of the carbonyl. And when this happens, it makes it even more polarized. So this is what you get. Now this is really delta minus. And any kind of nucleophile then is ready to attack. And so one of the common nucleophiles that we're talking about in chapter 10 is the Grignard. So a Grignard, let's look at a methyl Grignard. We're doing the Grignard reaction. So this is a positive, we see magnesium, and then the carbon is a negative. This, I told you, is a base. It's also a nucleophile. Now, in these conditions, and you don't even have to have protonation because it's so reactive. what'll happen here, this carbon nucleophile will attack the delta positive carbon. And when that happens, you make an alcohol. CH3, CH3, CH3. This is your CH3 here. This just added. And then this is your oxygen. And then this gets protonated. And what you do is you write 1. This is step number 1 across the reaction arrow. And then step number 2. So you look at 1 first. And then this is where you're adding your acid. So when you add H3O plus, which is hydronium, you see the pK is negative 1.7. So what's happening is now it's going to react with the Grignard magnesium and protonate that oxygen. And then you have to recognize that this is an alcohol. Okay, so we always have a functional group transformation. We went from, you need to recognize this and name it. This is a ketone, and this particular, the common name is acetone, or you could call it 2-propanone. See the O-N-E, ketone, O-N-E. So, and then what is this? Well, it's an alcohol. Whenever you get an alcohol, you classify it. So this carbon is connected to 1, 2, 3 carbons. So it's a tertiary alcohol. And that happens to be, if you find your longest chain, happens to be 2-methyl 2-propanol. Okay? So recognizing strong bases in reactions. So this is important. If I look at the past exam, we had which mechanism would you expect with the reaction of 1-methyl, 1-bromo, cyclohexane with potassium tert butoxide. Now, potassium tert butoxide, there's potassium, and this is tert butoxide. Oxygen minus, and this is your tert butyl group. So this is potassium tert butoxide. You've got to recognize that is a strongly hindered base. You have to memorize that and see that. Now that means we've got to see what our substrate is. So let's draw our substrate. And we see it's cyclohexane. So cyclohexane is this, cyclohexane, and then 1-bromo and 1-methyl. So this, you need to recognize this is an alkyl halide. You see it's an sp3 carbon bonded to a halogen. That makes it an alkyl halide. And when you get alkyl halides, to understand how they're going to react, you classify. So this carbon is connected to 1, 2, 3 carbons. So this is a tertiary carbon. Tertiary alkyl halide. Now, tertiary alkyl halides undergo SN1 only under acidic conditions, and E1 under acidic conditions. So what are the acidic conditions? Would be like sulfuric acid, or you would get, or even neutral conditions. They're also neutral. What's a neutral condition? Just methanol. That could be sovolysis. Water. You notice they don't have a negative charge. The negative charge makes it all of a sudden methoxide. Now you have strongly basic conditions. The reason why you get the 1 under these H3O plus hydronium type acidic conditions, you have to stabilize a carbocation. Okay? Carbocations are not going to be stabilized under basic conditions. Okay? So, carbocation, choose the C plus, not under basic conditions. So if you have basic conditions, no, you can't get this. So you have to see that you have a strong base here. And this is a tertiary alkyl halide. These undergo E2. E2. And so this base will come and take that proton, and then you'll get a thing called dehalogenation. Essentially an E2 reaction. And this is a good reaction to understand because it's under basic conditions. And you got to understand that you're not going to get a carbocation under basic conditions. And that's a good reason why you got to recognize when you have strong base. Recognize an acidic protons in organic compounds. So the acidic compounds you've seen so far are the sp carbon hydrogen alkyne. You've also seen alcohols can be considered acidic protons, and but you have to have a very strong bases for both of these. Okay, very strong bases, the strong bases. So your strong bases need to be like sodium amide and sodium metal, potassium metals. Now the other ones we're introducing in this chapter are your phenols. Those have a pKa of about 10. So you just need a base. You don't even need a strong base. So potassium hydroxide will do this. The other ones we're going to talk about and you haven't seen yet, but I'm going to go ahead and introduce it because it's going to be important to recognize them because we're doing carbonyls. So this is a carbonyl. And you see, you probably recognize this is acetone. Okay, from the carbonyl position, this is an alpha carbon. So if you have something like this, and they rarely go past that, but this is considered alpha, this is your beta, and this is your gamma carbon. So you count down from this carbonyl. And of course, you have 2 alpha carbons here. These alpha carbons, these hydrogens, are acidic. These are acidic. Okay, so you're going to find several chapters where you can just take something like sodium hydroxide and you can actually deprotonate that. So that has like a pKa of about 20. So if you deprotonate that, you get something like this. And you don't have to do this yet, but we will at some point. You will get something like this, and you'll get water, and then you can compare that to 15.7, and that's a pKa here of 20. So a lot of times you use like potassium alkoxide, so like tert butoxide, and that pKa is about 16 or 18, and so and that's what you do. So actually, and also you can use sodium amide, and we'll talk about LDA. You'll see LDA, lithium diisopropylamide. So that is kind of like sodium amide, and that is a a base that you typically use, because if you use sodium amide here as your base, then you make ammonia, and your pKa there is 35. So this will, 35 versus a 20. So this will drive the reaction. So by choosing the strength of your base, you can drive your reaction to completion. Okay, understanding functional group transformations. This is where you have to really organize your reactions and see your functional groups, and you got to work on your naming. So when you see a compound and you see something that's an alkene, you need to recognize that, hey, there's an alkene. That's your only functional group. And then when you look at alkenes, you say, well, is that a trans? That's a trans. Or it could be a cis. And then that's when you look at, let's say MCPBA. We've talked about this. MCPBA is a peracid. And that peracid here will make an epoxide from alkenes. And that's something you have to know. Now, the key is here, it retains the same stereochemistry. So this is a trans epoxide. So when you're doing these transformations, it's important to name your starting material, alkene, and what you're making, epoxide. And there's your reagents. Now what's nice about MCPBA, it's done usually under neutral conditions. And that's important because your epoxide is base sensitive and it's also acidic sensitive. And so if you make your epoxide, let's do the cis here, and you use peracetic acid like this, then what happens is the first thing you're doing is you're making your epoxide, but then you also generate acetic acid, and acetic acid has a pKa of about 4.7. So what's going to happen is the epoxide is going to get protonated under these acidic conditions, and then the water, which is always around under acidic conditions, is going to come and open. Now, of course, in this case, both of these are equally substituted, so you're probably going to get a mixture of product, which will be this anti-diol type substrate. Okay, so under basic conditions, your epoxide is going to open from the least hindered. So that's why it's important when you're doing these to classify what functional groups you have. So when you do stuff like we've talked about ozone, so ozonolysis, and then you add DMS and water. Dimethyl sulfide actually breaks up the ozonide. Well, what happens here is you got to say, oh, okay, I have an alkyne, and alkyne ozonolysis. Ozonolysis. That is going to split using ozone. And it's going to split right there at your function, at your alkyne function. And in this case, it's going to give you a carboxylic acid, and then the terminal one will go on to be CO2, which is fully oxidized carbon. But if you have an alkene and you do the same conditions, you get an aldehyde and a ketone. So This is that carbon here, and this is that carbon here. Okay? So this is why it's important to know, okay, on ozonolysis, I'm going from an alkyne, and you say it, I'm an alkyne, and I'm going to get carboxylic acids. Okay? So what I want you all to start doing is, for each index card, we're going to do one reaction. We're going to learn just a few a day. Here we have an alkene, and we're going to a ketone and an aldehyde. And that would be formaldehyde, because there's only one carbon there. CH3, that would be, because there's two here, acetaldehyde. The name is important. Okay, so these are just some of the slides that I've pulled from chapter 9. As you can see, what's happening here is just comparing different compounds. So this is just a regular alkane. So this is ethane. And an ethane hydrogen here, this bounded sp3, has about sp3, it only has 25% character, S character, has a pK of 50. So we would consider this not acidic proton. This is not an acidic proton. Okay, this is an alkene. So that proton there has 33%, and even though it's more acidic than an alkyne, it's still not acidic. You don't have a base that can pull that proton to make that negative carbon. See, when you make a negative carbon, now you have a reactive species that can go on and do reactions to make carbon-carbon bonds. Ammonia is pH of 35. The alkyne proton here has a pH or pKa of 25. So now very, very strong bases, very, very strong, what do we call it, strong bases, such as LDA, sodium amide, okay, these can remove that proton, that acidic proton. Alcohol has a pK of 16 to 18, so your strong bases, call these strong bases, can remove that proton. Something like sodium hydroxide and potassium hydroxide. Actually, they're not the best. Your strong bases, use sodium metal, potassium metal, and sodium hydride. Those are the reagents you would want for your alcohol proton removal. Okay. Okay, so this is a slide in your chapter. The pK ranges of alcohols are 15, so I said about 16 to 18. And you don't have to get specific. If it's 16.5, 17.8. Acidity decreases as the substitution. You don't even need to know that because we're not getting that close. Halogens and other electron withdrawing groups increase the acidity. That's okay. We don't need to know this. You do need to know that phenol is 100 million times, 108, more acidic than cyclohexanol. So what's a phenol? Phenols are OHs connected to the aromatic, and cyclohexanol is without the aromatic. So this is an sp3 carbon. This is an sp2. Now what happens is, so when you have something like sodium hydroxide, deprotonates that proton, you generate the phenoxide. So you generate the sodium phenoxide. And the reason why it is more acidic is because of resonance stabilization. So when you draw these resonance structures, those electrons go there. Everything is sp2. So and basically you have this here, And you are going to need to be able to draw these. So, and you draw the resonance as a double-headed arrow. And then this goes here, and then those go to that carbon. So maybe we'll practice this week, drawing some of these resonance structures. It goes there. It gets a negative charge. And then we're going to draw more. And the more resonance structures you can draw on an organic molecule, the more stable it is. And this is one of the reasons why, this is the reason, you put these in brackets, that phenoxide is very acidic. So 1, 2, 3, 4 resonance structures. So here's more in chapter 10, where you have the different pKa's. You see methanol and ethanol. Phenol is a pKa of 10. These alcohols, if you can see they're anywhere from 16 to 18, water's 15.7, acetic acid is 4.8, and hydrochloric acid, which is very acidic, is -7. Formation of alkoxide ions. So when you take an alcohol, this is what alcohols do in the presence of sodium. They form sodium alkoxide, and they give off hydrogen gas. The pKa is about 35 for hydrogen. The pKa is about 16. So this is why you're going to get the sodium ethoxide here if you put ethanol and sodium metal. More hindered alcohols like 2-propanol or 2-propanol or tert-butanol, and you add the metal, sodium, react faster with potassium than sodium. So that's why typically you end up getting potassium tert-butoxide for these substituted. And that's potassium tert-butoxide. So when you see how to make these, you put in your alcohol and you put in your metal, and you're going to make a strong, this is a very, very strong base. Very, very strong base. Phenols, these are phenols. Here, you can just use something, it's just a strong base. Okay, not a very, very, very strong base, just a strong base. And because the pKa is lower, pKa of 10, this is your acidic proton right here, the OH minus is going to deprotonate that and make water. And that pKa is 15.7. So 15.7 is about 6 orders of magnitude larger than 10, pKa of 10. So it's going to go 1, 2, 3, 4, 5, 6 times to the right. And we talked about how it delocalizes the negative charge through drawing resonance structures. And that would be its conjugate base, and the conjugate base is more stable. This is showing you the resonance structures that I was drawing, and as you move them, there's 4 of them. We drew 4 on the slide before. The true structure is a hybrid between the 4 resonance structures. Now, carbon is negatively charged when it's bounded to a metal, organometallics. So we've talked about this. So when you have carbon bonded to a metal, you need to go ahead and find that metal, magnesium, and make it positive, and the carbon negative. You can also see this with lithium. You'll see lithium binds to carbon, and this makes lithium positive and carbon negative. If there is no acidic protons in solution, These are great nucleophiles. And they particularly will go after a carbonyl. It's typically how you use these nice Grignards. That's a carbonyl, and it will go after that positive carbon. So that's why you usually use THF, tetrahydrofuran, or diethyl ether. These do not have any acidic protons. So here you're showing, we're talking about acetylides, and the acetylide will undergo an SN2 reaction over an alkyl halide. This is the primary. Now when you have these are strong bases, and they're great nucleophiles. So if it's a strong base and a great nucleophile, then you want to react them with a primary alkyl halide. Otherwise, you're going to get some E2, and you don't really want E2, so you get that with secondary. This is showing you acetylide attacking a ketone or an aldehyde, and then you make an alkoxide that then under a pH of, or pKa of, was it 1.7 for hydronium? You protonate that alcohol, and you get a acetylenic alcohol. Terminal alkynes can be converted to sodium acetylides by strong, very, very strong bases like sodium amide. They're useful nucleophiles, but only if there's no acidic proton around. That's why you got to recognize if you have an acidic proton. Grignards, remember this is the Grignard I'm typically right, methyl Grignard, and organolithiums are good nucleophiles, but also in the presence of acidic protons they will act as strong bases. So this is where you find them. A hydrogen bonded to an oxygen, hydrogen bonded to a nitrogen, a hydrogen bonded to a sulfur. This is your acetylide, a terminal, the CC hydrogen. Also in the presence of multiple bonds, they will act as a nucleophile. So this is a carbonyl. You'll see this as a nitrile, and sulfurs and nitrogens. And so hopefully you've gotten something out of the importance of recognizing acidic protons and recognizing strong bases and can apply that.